is also the title of today's seminar. Okay, so prove complexity as a computational lens. I'm Jakob Nordström at the University of Copenhagen and Lund University. And as a warm-up, let's talk about three problems that's going to follow us today, just to check that we're on the same page. So we have a graph, something like this. And a valid, legal coloring of this graph is you color all the vertices in such a way that all neighbors, all vertices connected by an edge, have distinct colors. And of course, we want to use as few colors as possible. And you can see that you can get away with 3 colors for this graph, but not 2 colors. And you can see this, well, because there's a triangle, lots of triangles in this graph. So you will definitely need 3 colors. Hopefully you'll know. Most of you will know this problem. Another problem that most of you will know is clique. So now we're looking to find a number of vertices that are all pairwise connected, the clique. We want the clique to be as large as possible. Since there's a triangle, we can find the 3 clique. And you can look at this graph now and think for a while, and you realize that 3 is the largest clique we can find in this particular graph. The third problem we're going to think about is the Boolean satisfiability problem, given a formula in propositional logic, something in conjunctive normal form, like this formula here. Is there a way to set the variables, assign the variables to satisfy all the constraints? So what does this mean? Variables should be assigned true or false. And a constraint like the third one here should be read as x or not y or z, means that either x or z should be true or y should be false. And we're looking for a truth value assignment that satisfies all constraints simultaneously. This is what this these ands mean here. So these are the 3 problems we care about today. We are super happy to just look at them as mathematical problems, but they're also come up in applications for coloring, things like frequency allocation. The clique problem is all over the place in bioinformatics. And why do we care about SAT, the more abstract problem? Well, because SAT can model this problem and many other problems in computer science, like hardware and software verification, problems in artificial intelligence, operations research, cryptography, bioinformatics. The list really goes on and on, except that in real-world applications, we will not have the kind of small toy formulas as you saw on the previous slide. You should think of formulas with maybe 100,000 variables, maybe 1 million variables. And the question is, how can we solve these formulas efficiently? How can we decide whether they have satisfying truth value assignments? Not by pen and paper, so we want to use computers. Can we do this efficiently? Turns out that this is a question that has been studied ever since the dawn of computer science, even before computer science. Gödel and von Neumann were corresponding about it. There's been a lot of research about this. Cook and Levin proved in the 70s that this is an NP-complete problem, which probably means, for all we know, that it's very hard to come up with algorithms that always work, always run fast, always give the right answer. In fact, we know more about these problems today. We know that assuming that P is distinct from NP, which most people believe, it's not even possible to approximate how few colors you need or how large a clique is, to distinguish between where the clique is like essentially all of the graph or nothing of the graph. And we also know that it's very hard. You can't really do better for a Boolean satisfiability formula in conjunctive normal form than seeing whether basically a constant fraction are satisfiable or not. For 3CNF, you cannot go above 7/8 as a result by Hostad. That's what theory tells us. In practice, we have a very different picture. There are good algorithms that solve even non-trivial coloring instances efficiently, as is the case for clique. And for SAT solvers, there are truly amazing so-called conflict-driven closed learning or CDCL SAT solvers developed since the turn of the millennium that do solve efficiently CNF formulas with millions of variables. And so one thing that is of interest, how can we understand these algorithms and when and why they work for these problems, these NP-hard problems that we believe in theory are very hard. And what is going to be the focus on this lecture is we'll try to use tools from proof complexity to shed light on these type of questions. To be clear, this is not the only way in which you could try to analyze this type of algorithms, but this is what we're going to do today. So how do you connect combinatorial solving and optimization, which are the kind of problems we talked about before, to proof complexity? Well, if you have an algorithm, you can try to abstract away what kind of reasoning the algorithm performs, and then try to describe this as a formal method of reasoning or a formal proof system where every single step that the algorithms perform, you can check that this step is valid. That means that the algorithm execution can then be described as a sequence of such reasoning steps. And now you can ask two questions about the efficiency of an algorithm when given a certain problem to solve. The first question is there in principle a short sequence of reasoning steps that will lead to the right answer? And in this formal proof system, we can view it as, is there a short proof of what the right answer is? And then the second question is, given that there is such a short proof, is there a way algorithmically to actually find such a short proof that would make the algorithm run fast? What we're going to focus on today is the first question. In principle, just abstract away all questions about constructiveness and just think about these methods for combinatorial solving and understand what they should be able to do or not do in principle. And one important thing to note here that this means that we're kind of analyzing optimal algorithms. We're not really concerned about how to find these reasoning steps. We're just assuming that the algorithm can somehow magically always make the best choice. And still, even for such algorithms, we are going to try to pin down limitations on what they can do. This immediately means for CNF formulas, for instance, that we're only going to focus on unsatisfiable formulas. Why? Well, because for satisfied formulas, it's clear what an optimal algorithm could do. It could just guess, zoom in magically on a satisfying assignment, check that it is a satisfying assignment, and it's done. So we won't be able to prove any lower bounds on how quickly you can find a solution. But what we can look at is, suppose that there is no solution, suppose that we get an infeasible problem, how hard is it to find a proof of infeasibility? And that's what we're going to talk about today. The second question is also interesting, like given that in principle a method of reasoning can solve a problem efficiently, can we turn this into an algorithm? This is a deep question with lots of exciting recent progress. And mostly negative results. In the technical terms, these are non-automatability results, showing, for instance, that even if modern methods used for Boolean satisfiability solving or algebraic reasoning could be efficient in principle, making them efficient with worst-case guarantees is often as hard as solving NP. But I won't really talk about that today. So we'll focus on the question of what you can do in principle in terms of the strength of the method of reasoning. And today we're going to have this applied focus on proof complexity. To be clear, something that I'm not talking about, there are lots of theoretical reasons to do proof complexity also, but three applied reasons why you should care about proof complexity is what we started talking about now. It gives us a way to understand real-world algorithms for combinatorial solving. Once you have this understanding, a second reason is that, as shown in these example references here, this understanding can sometimes help you to see, once you understand the algorithm, find ways to improve it, where you realize that the algorithm is maybe not exploiting the full potential of the method of reasoning that it's using. And a third potential application of proof complexity, which I'm personally very excited about, is that once you understand the method of reasoning an algorithm is using and can formalize it, you can also use this to actually enhance the algorithm to write a machine verifiable certificate of correctness, so that it not only solves the problem, but gives you a proof, a mathematical machine verifiable proof of correctness. And I'm dumping some references on this slides, but we're not going to talk about this today. And for the rest of, mostly for the rest of today, maybe, but also for the following lectures in this proof complexity course, we'll just say, actually, even without all of these applications, we just get a lot of really nice mathematical problems that we can do discrete mathematics about, and we don't really need any further excuses than that because we like to do discrete math. Okay. But again, today I'm going to try to elaborate a little bit on these connections, and then in follow-up lectures on this course, there's going to be more about the math. So today I'm going to spend maybe half of the time to talk about SAT solving. I already mentioned conflict-driven clause learning. Before that, there's the DPLL method, and it turns out that they're both modeled by this resolution proof system, which is arguably one of the, or the most studied proof system in all of proof complexity. And then I'm going to spend some time on algebraic proof systems, such as Nullstellensatz and polynomial calculus, which is connected to Gröbner basis computations, just to mention the buzzword. And then there's also the cutting planes proof system, which is connected to pseudo-Boolean solving. And then towards the very end, depending on how we're doing on time, I will probably say something very brief on more advanced proof systems such as Sherali-Adams and sums of squares, where you go into hierarchies of linear programming and semi-definite programming, the stabbing planes proof system, which is connected to mixed integer linear programming, and also a little bit about the extended resolution proof system, which is needed to model everything that SAT solver can do. So this is the plan. This is the outline for today. And you can interrupt me with questions at any point. I'd be happy to try to elaborate on anything. The point of this is we have lots of slides to go through, but the point of this exercise is not to get through the slides, but to try to convey information and clarify when needed. Okay, so this is the plan. Just to fix some terminology or notation, we're going to talk mostly about formulas in conjunctive normal form. Those are conjunctions of clauses, where every clause is a disjunction of literals, that is variables or negated variables. And from now on, I'll write negation with overline or with bar. And the variables take values true and false, but I'll throughout this talk, I'll identify true with 1 and 0 with false. Okay. Also, some other things. Sometimes I'll talk about K-CNF formulas. That's formulas where all clauses contain at most K literals. We usually think of K as a constant. And sometimes to distinguish when we have proof systems that derive new clauses, we talk about the original clauses in the input CNF formula as axioms. Whenever you see a capital N in these slides, this is typically the size of the input formula, which we can define as the number of literals in the formula counted with repetitions. And also, just to make 100% sure we're on the same page, we're also going to use standard asymptotic notation. Like big O, it says that something is big O Fn if it's asymptotically grows at most as quickly as Fn, and it's big omega of Gn if it grows as least as quickly as G of n, and theta of Hn is when H exactly describes the asymptotical growth of the function we're interested in. Okay, so with these preliminaries out of the way, we can now formally define the SAT problem as you're given a formula F in conjunctive normal form, something like this. And the question that we're supposed to decide, this is a yes/no question, is there a satisfying assignment or not? And so we can think about this, and we can think, what about setting all the variables true? Maybe you see that this won't work because, for instance, this clause here wants at least x, not x or not v, wants at least one false literal. For the same reason, setting all variables to false won't work because the first clause x or z wants at least one true variable, one true literal, one true variable. And the question is now, can we somehow assign these variables x, y, z, etc., in some smarter way to make the formula satisfying? And this is a question that we're going to ask ourselves. We're going to answer this question in just a few minutes. But before that, I want to say something that we're going to use today is also that we can express this Boolean satisfiability problem in different ways. For instance, I could rewrite these clauses as a collection of polynomial equations. thinking of, again, 1 as true and 0 as false, you see the first clause x or z, I could write as if I multiply 1 minus x and 1 minus z, I should get 0. And the second clause, y or not z, becomes the constraint that 1 minus y times z should be 0. So if you think about this for a while, you see that the CNF formula has a satisfying assignment if and only if this set of polynomial equations has a common root. And I can simplify and write it up in this way. So what I want to convey to you that hopefully we all agree that this set of polynomial equations is in some sense the same problem as the CNF formula. We can also write it as a set of linear inequalities where saying that x or z holds, I can just sum up x and z and say that the sum should be at least 1. And again, that y or not z should be true. It's just saying that y plus 1 minus z is greater or equal to 1. Again, I'm restricting myself to 0, 1 solutions here. And then we can simplify this. And then I hope we can agree that the CNF formula is essentially the same problem as this set of 0, 1 integer linear inequality. So we'll use this throughout this talk, that we can shift between this syntactic view of the problem as a Boolean formula or as a set of polynomial equalities or a set of linear inequalities, and ask about 0, 1 valued solutions to this problem. And just to show how we can also model these problems that I mentioned in the beginning and that we're going to talk about also as throughout the lectures in our examples, the clique formula asking whether a graph has a clique of size m can be modeled with variables q, k, I, which basically says qki says that vertex I is the kth member of the clique. So we have a first axiom saying that some vertex has to be the kth clique member, that it is uniquely defined, that I'm not counting any vertex several times. And then the most important constraint is that, well, if two different vertices u and v are in the clique, then they have to have an edge between them. So for every non-edge in the graph, I encode a constraint. If u, v is a non-edge in the graph, I encode a constraint saying that u and v cannot both be in the clique. In a similar way, the coloring formula saying that the graph has a valid m coloring, we have then axioms or constraints saying that every vertex should get exactly one color. And for any vertices u, v connected by an edge, we don't want them to have the same color. Okay, so these are, and it's hopefully I'm sort of going a little bit slowly over this just to make sure we're all on the same page, but solving the clique problem or solving the coloring problem for a graph is essentially the same thing as figuring out whether these formulas have satisfying Boolean assignments or not. And by the translation we have on the previous slide, we can also view these problems, if we want to, as polynomial problems or as 0, 1 integer linear inequality. And I should also say that this is not, if you actually wanted to solve, say, clique with a stat solver, you would probably not maybe pick this encoding. There are smarter encodings out there, but these are sort of good enough for us today to convey most of the what we need to know. Okay, so suppose you're given the formula like this, or our example formula, and suppose we go back to the 60s, how would you have solved this problem? Well, you would have used the Davis, Putnam, Logeman, and Loveland, or DPLL method, which is basically the following. It's a recursive method. So you somehow, there's a base case that you're going to assign variables and then simplify clauses by removing literals from them. If you ever find that you have removed all falsified literals from a clause, then you falsify it, you have an empty clause contradiction, this is a conflict, and you have to return from that recursive call. If you have satisfied all the clauses, then you know that you've found a satisfying assignment and you can terminate. Otherwise, what you do in some clever way, you pick a variable x, you try to set it to 0, to false, you simplify the formula and make a recursive call. If that fails, you try instead to set x to true, to 1, simplify the formula and make a recursive call. If both of these cases fail, then you know that there is no satisfying assignment because x would have to be either true or false, and then you can return. So just to see how this would work on our example formula, I want to visualize the algorithm execution as a search tree. And then we're going to, what do I mean by simplifying the formula? Well, if a literal in a clause is satisfied, then we can remove that whole clause. We don't need to worry about it. If a literal in a clause is falsified, then we can remove that literal because we're not going to satisfy the clause with the help of this literal. So suppose we start branching on x and we set it to false, then we see that we can remove x from the first clause and the third clause because x is not going to help us satisfy these clauses. This sixth, I believe, and eighth clauses, we don't need to worry about those because x is false, so these literals are true. Okay, but there are no empty literals, there is no conflict, so we have to branch on something else. Let me branch on y and set it to false. Then we see that clause number 3 and 4 are now true, and still no empty clauses, and now we maybe branch on z. And then we see that if we set z to false, then that violates the first clause, so we have a conflict. We go back and we try the other value for z, but that violates the second clause. So now we tried both values for z and nothing worked. So the mistake must have been for y. So we go back and try to set y to true instead. And then maybe we try to set u to false, but that violates the third clause. So we have to try to set u to true instead. That violates the fourth clause. Now we've tried both values for y. So our mistake must have been to set x to false. So now we know that x has to be true. And now, we don't want to spend the whole afternoon on this, but let me just run through quickly the rest of the example. That now I might set x to true, and then u to false, and v to false. Again, I hit the conflict, so I try to set v to true instead. That doesn't work. So I go back and try to set u to true. But again, if I do this, then w being both false and true doesn't work. So this is a DPLL execution that shows now that this formula was in fact unsatisfied. Okay, and this is essentially how SAT solving was done up to somewhere around 1990. Except I didn't tell you about how did we pick these variables. Are there smarter ways? And incidentally, one thing that you will realize, if you go back here, I think you realize that when the formula looks like this, it doesn't seem terribly smart to branch on y. I could already force a contradiction on z. Because there's only a single literal left in the first clause. That's called a unit clause. So I should probably have branched on z here. And indeed, any decent DPLL implementation would have branched on z here, but then I wouldn't have gotten this nice search tree. So I'm skipping things like this. Okay. So if we fast forward to today, what do so-called conflict-driven closed learning solvers do? Well, they still try to build a satisfying assignment. And how to pick the variables, the branching or decision heuristic is crucial. One thing they do when they hit a conflict, they don't just backtrack, but they will compute a reason for why the current partial assignment failed. This reason will be a new clause that you will actually add to the formula. And the idea is to avoid making the same mistake again. And then every once in a while, somewhat mysteriously, it turns out to be a super crucial feature of modern SAT solvers to just start over from the top. Ignore where you are in the search tree, start over from the top. Except keep the clauses you have computed. Why is this super important? In fact, we don't know whether these restarts increase the reasoning power of SAT solvers or not. That's a big open problem. Probably I would guess that it does, but we really don't know. And we're not going to talk about it today. I will try to just illustrate how a modern SAT solver works on a small example. So I've expanded the formula a little bit. And the idea is that if you basically get this example, then you know most of the secrets of modern SAT solving, except I'm not telling you about all exactly the heuristics, but this is really what would go on under the hood in a modern SAT solver. So we have to we're starting by building a partial truth value assignment by making assignments. There are two types of assignments. Right now, there's zero information here, so we just pick a variable and set it to some value. A modern SAT solver might typically pick the first variable and set it to false. Why not? Okay, and I'll make a notation here. I'm building my partial truth value assignment, and I'll just let this denote that P is set to false, and it's a decision. It's a free decision. But once I've set P to false, you realize that this first clause here, when P is false, U has to be false, or else I've screwed up this clause. This is what we didn't do before in our DPLL example. So once P is false, I should propagate U to be false, because otherwise I know that P or not U will be false. So I propagate U and I call P or not U as the reason clause for this. And a modern SAT solver will always propagate and only make a new decision once you've done all the propagations. Here it turns out that there are no further propagations. So let's decide on the next variable Q to false. Now the second clause propagates that R has to be true. Now the third clause propagates R or not W, propagates that W has to be true. There are no further propagations, so we have to decide again. The next free variable to decide on is X. Let's set X to false also. Now it gets more interesting. Since U and X are both false, this clause propagates that Y has to be true. But then this clause propagates that Z has to be true, and this makes the clause not Y or not Z very unhappy. Okay? So a SAT solver will do this. It will decide on variables, and then it will do propagations until either you have satisfied all the clauses, or as happened here, we run into a conflict.
Is there a reason why you always decided to put false first?
I just did it because the very famous mini-SAT solver decides on setting variables to false. But no, and in fact, like if we were like one of the most important heuristics in a modern SAT solver, if you're in the middle of the search, you have to have an intelligent, you have to do two things. You have to pick a good variable to branch on, and then you want to pick whether you're setting it to true or false. And there are like advanced heuristics for this that I won't talk about.
You've never done it random?
Random is pretty terrible. You could ask like, okay, should I do like a, maybe a small fraction of random decisions? To the best of my knowledge, there is like, I think people tried this out before, but modern SAT solvers are basically fully deterministic to the best of my understanding. So like randomness doesn't help you.
Mm-hmm.
But you have sophisticated heuristics that try to pick up information about what is a good value. But this would be another lecture. Okay. So we have a conflict now. If we were running DPLL, we would just go back and try to set X to true instead. Okay, but we want to do something smarter. Oh, one more thing that I should say. So some SAT terminology, just, after this slide, you're done with CDCL, everything, except you also need to know about decision levels. What is a decision level? A decision level is the assignment, the decision, maybe I should point here because it's easier to see, followed by all propagations. So this decision and this propagation is decision level 1. Here we have one decision and two propagations that are decision level 2. And then we reach a conflict at decision level 3. Is the fancy way of describing what happened here. So we reached a conflict at decision level 3. What do we do? So we are not just going to do DPLL. We want to compute what went wrong. Like, why does this assignment not work? Clearly not Y or not Z isn't happy, but can we say something more informative? Well, we can look at the last two clauses, and we can say that not Y or not Z wanted Z to be false, but the reason Z wasn't is that the clause X or Y or X or not Y or Z wanted Z to be true. So we realize that if we just look at these two clauses and merge them and remove Z, the only way to make both of them happy is in fact to satisfy X or not Y. Okay? And this now is a new clause that isn't in the formula, but is implied by it. So any satisfying assignment to all of these clauses above has to satisfy this as well. And now we can continue and look at this clause wants Y to be false, but U or X or Y wanted Y to be true. So we can merge them and remove Y in the same way and learn that in fact U or X should have been true. And now again, I'm doing this a little bit quickly, but now the SAT solver will terminate and say, I want to learn this clause. Why does it terminate here? Well, because this is a unique implication point. There's only one literal at the last decision level. See, U is at decision level 1, X is at decision level 3. So this is a first UIP clause. This is the first unique implication point. We'll learn this, and now we'll just add this to the formula, and we'll clear our partial assignment, which is called the trail. And we'll remove as much as possible from the trail up to the decision level where this learned clause is still propagating. So we'll remove decision level 2 and 3. We'll keep decision level 1, which is shaded here. And now you see that given that P and U are both false, this learned clause propagates that X has to be true. And now you can say, wait, wasn't that what DPLL would have done anyway? And the answer is no, because we have note that we have gotten rid of the branching on Y, on Q. We've identified that Q wasn't even involved in this, and all propagations after Q were immaterial. The mistake was X. And so now now also the other difference from DPLL is that setting X to true is no longer a decision, it's actually a propagation. Okay, so now we revert to doing what we should do before. We just propagate for as long as there are propagations. Now not X or Z propagates, but that made not X or not Z unhappy. So now we have a new conflict. Now the conflict analysis is very simple. We see that we'll just learn that X has to be false. So by now the SAT solver has realized that in any satisfying assignment, X has to be false. And this is unconditionally true. So now we clear the whole trail and just assert that X has to be true by this new learn clause. This now tells us by U or X, which is this other learn clause here, tells us now that, well, if X is false, then U has to be true. But then P or not U says, well, if U is true, then P has to be false. But then we have a conflict with this guy. At this point, the SAT solver would stop because we've reached contradiction without making any assumptions. So we know now that the formula is unsatisfiable. We could still theoretically run a conflict analysis again, and let's do it because it will be nice to do proof complexity with this. If we did a conflict analysis just as before, we would learn that not U holds, and then we learn that X holds, and now it's clear that we've derived that X is both true and false. When we merge these two clauses, we get nothingness, contradiction. Okay. This is modern SAT solving. This is what these solvers do. The only thing I haven't told you about is sort of how you exactly when to terminate the learning, and it turns out that you can do it slightly differently, and we haven't talked about how to make the decisions. One other thing we didn't talk about is you will learn, like typically a modern SAT solver will learn something like, say, on the order of 50,000 new clauses per second. If you keep all of them, that's going to be a lot of space eventually. So you need some kind of way of filtering which clauses you want to keep long term. I haven't told you about that either. But apart from this, this is like modern SAT solving. And in one sense, it's amazing that something so simple can be so super efficient. And we'll get back to that. In fact, we'll get back to it now. So how can we understand these SAT solvers? Like how, and I already started telling you that, well, there are these, how do you branch, which clauses do you keep? Let's just ignore this and let's try to look at the fundamental, what reasoning is going on here. The reasoning is happening in the conflict analysis, and the reasoning is actually modeled by the resolution proof system, where what is the resolution proof system? Well, you have an input CNF formula with axioms again, and then you can derive new clauses by the resolution rule that says that if I have previously derived C1 or X and C2 or not X, then I can, this merge operation, I can merge C1 and C2 and remove X. This is saying that any truth value assignment that satisfies both C1 or X and C2 or not X has to satisfy C1 or C2. And note that importantly also, in order for this to make sense and in order for us to be able to derive contradiction, and I should have said this before, it was on the slide, but I didn't say it. I don't care about the order of literals in the clauses, and also there are no repetitions. So I think of the clauses as sets, and that is how they can shrink. This is like an important formula. Okay, now this is the resolution rule, and now the observation is that, well, if I start with the formula F and I don't know whether it's satisfiable or not, I can start deriving new clauses from it. And if I derive a new clause by resolution on two previously derived clauses and add it, the formula with this new clause added is still satisfiable because the new clause is semantically implied by previous clauses. So one way of proving F unsatisfiable, if I just iteratively apply the resolution rule until I derive something patently false, like X and not X. Okay, this will be a proof of unsatisfiability, and we'll also call this a refutation, a resolution refutation. And now the point is that DPLL executions are resolution refutations. Now, formalizing this would take us maybe 1 or 2 minutes. I'll just do a proof by picture. Look at this execution we had before. And now what we'll do that over each branching variable in a bottom-up fashion, we'll just apply the resolution rule. Okay, and now you see that X or Z resolved with Y or not Z gives us X or Y. X or not Y or U resolved with not Y or not U gives us X or not Y. And then I just apply the resolution rule for all the other internal nodes, the branching nodes, one by one, until finally I've derived X and not X. And then when I resolve them, there's nothing left. I get the empty clause, which we denote by bottom because it's contradictory. So now we know, again, that this formula is unsatisfiable. And the way I proved it is, well, any satisfying assignment to all of these 8 clauses, such an assignment would also need to satisfy the clause that doesn't contain any literals that could satisfy it in the first place, which means that the formula is. And what I claim without proof is that this works for any DPLL execution. It's not, there are some technical details to take care of that I'm trying to sweep under the rug, but nothing really important. And also one important thing is if you look at this graph structure of the proof, you actually get a tree-like proof where every intermediate clause is only used once, and then you can think of it as being discarded. This is called like a tree-like resolution derivation. This means that if I can prove a lower bound on the size, the number of clauses in a tree-like resolution refutation of a formula, this means that this gives me a lower bound on the running time of any DPLL algorithm, even one that makes optimal branching decisions. Does this make sense? Okay. But this is only DPLL. What happens with conflict-driven learning? Well, conflict-driven clause learning, then you don't get a tree. You will get some shortcut edges in your graph, but it will still be a valid resolution proof. And again, I'll do a proof by picture. Here is our CDCL execution. Let's focus on the conflict analysis, and let's string them together just by how learned clauses were used in later conflict analysis. And then you in fact get a valid resolution refutation. In this case, it's hard to make a good small example that isn't tree-like. So you see we got a tree-like resolution refutation here as well, but in general, that won't be the case. And again, this requires a proof, but it's not hard. And I would say if you just sit down for a few minutes, you would work out the details. Like everything I've told you I've told you everything you need to actually formally prove that from any CDCL execution, you can extract the resolution proof. With a caveat that I'll get to at the end of the slide. What this means is that if I have a lower bound on resolution proof size for general DAG-like proofs, not tree-like proofs, this gives me a lower bound on CDCL running. You can also ask, what about, so that the kind of resolution proofs that you get from CDCL executions that you could see, they will have a very peculiar structure. Now you can ask, what if I have a formula for which I have a very clever resolution proof that has a sort of very intricate structure that doesn't correspond to CDCL? Could the SAT solver still run fast? So this is a deep question that took quite a while to solve, but it turns out that yes, if there is a short resolution refutation of a formula, then conflict-driven clause learning has the potential to find maybe not exactly that proof, but some short. Okay, this is a theorem. However, if you want to do this with full algorithmic guarantees, then this is as hard as solving it. And this is what, in a formal sense, this is what was shown in this paper by Atserias and Miller, is that automating resolution or finding short resolution proofs efficiently is NP hard. So it's as hard as solving satisfiability in the first. The caveat here is that I didn't discuss pre-processing. So modern SAT solvers, before they even start this conflict-driven search and clause learning, they will apply all kinds of crazy pre-processing techniques to try to simplify the formula. Those are, not all of them at least, are not captured by resolution. However, you can try to, we'll soon discuss some theoretical formulas that are hard for resolution. And even though we cannot prove, and in fact, these formulas are not hard for the proof system that you need to model pre-processing, still in practice, it seems to be a pretty good proxy that if you have a strong resolution lower bound, then even a modern SAT solver with all kinds of fancy pre-processing in general won't solve it. In general, that clearly cannot be true in the sense that, well, if I know what the formula is, then you can always like have a pre-processing technique that detects this formula and sort of takes care of it. But in general, resolution lower bounds are a fairly good predictor of whether a theoretical formula is easy or hard. Okay. So, and the fact is now that SAT solvers are often amazingly good in practice. So SAT practitioners often think of SAT as an easy problem. And we can ask, can we somehow understand, get more of a theoretical understanding of why SAT solvers work and why applied instances are easy? This is another big open problem, and this would be really nice to understand this better, because in theory, we can show a lot of lower bounds for formulas that would seem to be fairly easy. And if such formulas are hard for resolution and hence hard for SAT solvers, then how can SAT solvers be so efficient in practice? Well, it seems like maybe these problems don't come up so much in practice then. So now let me review some theoretical benchmarks that are known to be hard for resolution. And these are, if you're going to follow the later theoretical lectures in this proof complexity course, these are things that we will prove later, but today we'll just state in the result. The most famous formula in all of proof complexity is the pigeonhole principle that says that n+1 pigeons don't fit into n holes if every pigeon wants its own hole, except that we want to do proofs of unsatisfiability, so we'll write down the CNF formula that says that this works perfectly fine. Every pigeon I gets a hole j, this is what this clause says, and then for two pigeons I and I prime, we don't want them to be in the same hole j. Okay, so these two, if you generate these two kinds of clauses, the pigeon axioms and the hole axioms, that's already claiming that there is a mapping of n+1 pigeons into n holes. That's unsatisfiable. Then you can also add so-called functionality axiom that says that every pigeon should go into exactly one hole. And maybe you can also say that every hole should get at least one pigeon. If you add these axioms, then you get the functional pigeonhole principle or the functional onto pigeonhole principle. That could just make the formula easier to prove unsatisfiable when you add constraints. But even the onto functional pigeonhole principle is hard. So resolution is a proof system that really cannot count. The proof requires exponential number of clauses in the number of holes and pigeons. If you look at the formula size, this will be exponential in the third root of the formula size, which again, what was formula size? The number of literals in the formula counted with repetition. Another formula that is even harder is the so-called Satan formula, which is essentially an encoding of the handshake lemma saying that the sum of the degrees of the vertices in a graph is even. So we have to somehow encode this in a slightly sneaky way. What we'll do, we'll give every vertex label 0 or 1 in such a way that the sum of all labels is an odd number. Then we'll make a Boolean variable for every edge, and then we'll write down constraints for every vertex saying that the parity of the edges incident to that vertex is equal to the label. Okay, so this would, for this graph here, we get these clauses just to see that around the one labeled vertex at the bottom, we say that x and u, the parity of them, should be odd. The parity of x, y, and w should also be odd. the parity of y and z should be even, and the parity of u, w, and z should be odd. And now by a simple counting argument, this has to be unsatisfiable, because if you sum up all the edges twice, you get an even number, but if you sum up all the vertex labels, you get an odd number. And we know that if you take a so-called expander graph that is very well connected, then this requires truly exponential lower bounds, exponential in the formula size, which means that not only is it the case that the resolution cannot count, it can't even count more. Another example is just randomly sampled KCNF formulas. For instance, if you randomly sample a 3CNF formula over n variables, we'll say 4.5 times n clauses. This is unsatisfiable with overwhelming probability, but requires exponential size in resolution. There are also other problems. We talked about coloring. The coloring encoding I showed you. There are graphs for which this is exponentially hard. And there are many other examples. The most up-to-date survey on results for different benchmarks is maybe the survey by Sambas and myself in the Handbook of Satisfiability. Interestingly, for the clique problem, there are strong reasons to believe that any algorithm should require, in the worst case, n to essentially n to the k, or n to the k except for some constants, or n to the omega of k. We do not know this bound for resolution. This is like a big open problem. We do know this lower bound for regular resolution, which is a resolution but with the restriction that I won't go into. But regular resolution we know is exponentially weaker than full resolution. For general resolution, the best bounds we have are for very large cliques. We get a 2 to the k lower bound, but not an n to the k lower bound. And again, for small cliques, we don't have anything. And basically for these large cliques, the reason you get a lower bound is basically for the same reason that you get the pigeonhole principle lower bound. So in that sense, you can even debate if it's a clique insight or if it's a pigeonhole principle insight. What would be really interesting for small or moderately growing k to get n to the k lower bounds, this is wide open for resolution. Okay, so we're done with resolution. And except for I want to have one final comment, is that how do we prove these lower bounds? Well, if you want to do it in the most efficient and generic way and like general way possible, then in fact you should not look at the number of clauses in a proof. You should not look at the size of a proof. You should look at the width, which is the size of clauses in the proof. And there's a result by Benstason and Vigdarsson that says the following: if I have a KCNF formula over n variables, and if I can prove that in any resolution refutation, I don't know anything about the length of the refutation, but I can prove that there has to be somewhere a clause of at least linear size, then this implies an exponential lower bound. This is a general result, and once you know this, to prove resolution lower bounds, you just have to prove width lower bounds. And this is a reason why we're interested in also studying width for resolution. There are also other measures that you can study. Space, which is a way of defining how much memory you need to present the proof. I won't define it now because it's a little bit complicated. You can also define the depth of proof, which is basically when you view the proof as a directed acyclic graph, what is the longest path in it. And there are also papers that study these measures and how they are related to each other. This is what I wanted to say about resolution and about stat solving. And now I think we are maybe roughly halfway through. So this might be a good place for a break. If we could hit the... So we're back after the break. So we talked about the resolution proof system, about modern Sat solving. Now we're going to talk about algebraic methods, Nullstellensatz and polynomial calculus, how they're related to Gröbner basis. So recall that if we have a CNF formula, we can take a clause and just translate it to polynomial equations. So every positive literal xi in the clause turns into a factor 1 minus xi. Every negative literal xj, not xj, turns into a factor just xj. And saying that the clause should be satisfied is the same as saying that this polynomial should vanish. Now, we could do this over any field. And so to be sure that we only get 0, 1 valued solutions, we should also add so-called Boolean axioms, xj squared minus xj for all variables. And now for any such system of polynomial equations in our favorite field f, which could be any field, then clearly, if I could find polynomials q and r such that when I multiply pj by qi, pi by qi, and then I multiply the Boolean axiom for variable xj with rj, if I sum all of this up and make cancellations and I get a 1, then clearly this shows that this set of polynomial equations is not satisfiable, does not have a 0, 1 valued solution. Because for such a solution, the left-hand side would vanish, but the right-hand side clearly never vanishes. What Hilbert's Nullstellensatz tells us, a slight generalization of the Nullstellensatz, is that this is actually an if and only if. If a system of polynomial equations with Boolean axioms added is infeasible, then there is such a Nullstellensatz certificate. This requires a proof that I'm not going to do. So we can view such a certificate as a formal proof. We can view it as a Nullstellensatz refutation. And for such refutations, we'll expand all polynomials out as sums of monomials, and we will consider the size of a refutation to be the number of monomials. And we're also interested in degree, which is the largest total degree of any monomial that appears, or any polynomial that appears in the certificate. And just to show how this works, here's our favorite CNF formula again. If I translate it to polynomials, this is what I get. Now I need to find, I can add Boolean axioms, except I won't do so here because they don't fit on the slide. And if I can now find polynomials so that when I multiply, here are these red polynomials appear magically. Now it turns out that if I would just do all of these multiplications, multiply out, sum things up, take cancellations, then I get a 1. So this is a Nullstellensatz certificate that this CNF formula is unsatisfiable. And just to see how to expand things out, I'm doing this a little bit fast, but hopefully there are no typos here. But if I expand it out, I claim that the size is 27 and the degree is 3. To see this, this is the expansion, and you can count to a total of 27 monomials here. And clearly the highest one has the degree 3. And now it's maybe not so clear that they cancel, but if with some color coding, you will see that you will find an orange and turquoise copy of every monomial that match up and cancel each other. So turquoise is positive and orange is negative. Interestingly, here I'm not using the Boolean axioms. So I don't need to use them for completeness for CNF formulas, but for other types of, you can define this proof system for any type of polynomial equations, and then you might need the Boolean axioms. Also, for some CNF formulas, having Boolean axioms can give you shorter certificates, but we're not going to talk about that. Okay, so this is Nullstellensatz. How would we find a Nullstellensatz certificate? Well, you can just set up a system of linear equations to find these polynomials p and q. And this is, in fact, what turns out to work really well for graph coloring. But the running time, the reason, and one reason to care about the degree, when you set up this system of linear equations, the size will scale exponentially with the degree. So if you require high degree, then this will take a lot of time to find these Nullstellensatz refutations. And this is, in general, not the best way to find Nullstellensatz refutation, because we know that there can be refutations of very, very high degree, but that are very sparse, very few monomials. So there's no connection in Nordström between degree and size in general. One other annoying thing with Nullstellensatz, if you look at a clause such as x1 or x2 or x3, and you take our translation and expand it out, then you see that you get, and in general, for any clause with a lot of positive literals, you get an exponential explosion in size when you translate it to polynomial. And that's kind of, on one hand, that's great because we want to get exponential lower bounds, but we're sort of getting them for the wrong reason. So one way to deal with this, at least when you're doing theory, is to introduce dual variables, or twin variables. So for every xi, I also introduce an xi prime, and then I add polynomials saying that xi and xi prime take opposite values. And this will allow me to translate any clause to a single monomial, where basically I use these prime variables for positive literals. So instead of 1 minus x, I just write x prime. For negative literals, I use the same translation as before. Clearly, this doesn't affect the degree at all, but this, in terms of size, this gives you an exponential improvement. So with these dual variables, you can get exponentially smaller proof. If we take another look at Nullstellensatz, what is Nullstellensatz saying really? Well, the Nullstellensatz certificate says that if a set of polynomials doesn't have 0-1 valued solutions, that happens if and only if one lies in the polynomial ideal generated by these polynomials. So what's a polynomial ideal? Well, it's just it's a ring. So it's closed under addition. If P and Q are in the ideal, then P plus Q are in the ideal. But it's also closed under multiplication by any polynomial R. And really what the Nullstellensatz certificate gives you is a certificate that one is in the ideal generated by the polynomials. But now you could potentially compute such an ideal step by step instead by quote unquote multivariate division. And this leads us to our next proof system, which is called polynomial calculus. But in order to describe this, let me first say like a quick detour about Gröbner basis. So we're going to have like 2, 3, maybe slightly technical slides. If you get lost, it's no problem. I can tell you when you should wake up again. Okay, so in order to talk about Gröbner basis, we need admissible orderings on monomials. So an admissible ordering is an order on monomials such that if m is less equal m prime and you multiply by any other monomial or term, then it doesn't change the order. And also, if you take any monomial and multiply it by a term, that can't make the term smaller. And examples of orders that you can use is you can sort lexicographically, or you can sort by degree and then lexicographically. There are also other orders that you can use. Once you've committed to an order, we can find the term in the polynomial that is largest with respect to this order. And this is the leading term. So we can write P as the leading term of P plus the rest. And now, if it so happens for two polynomials P and Q, that the leading term of P is divisible by the leading term of Q. So the leading term of Q times some other monomial T is equal to the leading term of P. Then we can reduce P mod Q by multiplying Q by this term T and then subtract. And note that this will remove the leading term of T. And what I meant by multivariate division within quotes is if you have a polynomial P and you have a bunch of other polynomials in a set fancy G, fancy style G, then you can do multivariate division where you just take P, and if there is a polynomial in G whose leading term divides the leading term of P, then you reduce. Now you get a new polynomial, modified polynomial P, and you try to reduce again, and you do this until you cannot reduce P any further. And that is the result of multivariate division. Okay? Except in general, the end result is not uniquely determined, because in which order you reduce can affect the end result. However, we say that a set of polynomials G is a Gröbner basis if this algorithm that I'm describing to you by vigorous hand waving, if it's guaranteed to give a uniquely determined final result, then that's a Gröbner basis. How do you compute a Gröbner basis? You can use Buchberger's algorithm, which is a very rough description. Basically, you take G to be all the input axioms, all the input polynomials, and now you just generate all pairs of polynomials, and you put them in a queue. And you just dequeue each pair PQ one by one. You take the leading terms and you compute the least common multiple of the leading terms. So you compute, you multiply P by some term TP and Q by some term TQ, so that the leading terms of these new polynomials cancel. Okay, and then you take this polynomial, so you multiply P by TP to get P prime and Q by TQ to get Q prime. You subtract, now the leading terms cancel, and you take this resulting polynomial S and you reduce it modulo everything in your set G with this multivariate division. If it turns out that the result is non-zero when you're done reducing, you add this to G, which will also obviously add, then you need to add new pairs to your queue. Okay? You do this until you've emptied your queue. The end result of this is guaranteed to be a Gröbner basis, which requires a proof. Another thing that requires a proof is that the field identity element 1 will be in the Gröbner basis if and only if the set of input polynomials is infeasible. Again, all of this very clearly requires a proof, but it's a mathematical. So now we can model this as a proof system that's called polynomial calculus, which is basically just computing elements within this IDEO. So what can we do? We have axioms that are the input polynomials, the Boolean axioms, and the complementarity or negation axioms. And then for any polynomials P and Q that you've derived already in the IDEO, you can take a linear combination alpha P plus beta Q for alpha beta in your field. And you can also take any polynomial and multiply it by a monomial. You have axioms, you have linear combinations and multiplication. This is the polynomial calculus proof system. And a polynomial calculus refutation is any sequence of such step that derives 1, showing that the set of polynomials is infeasible. And again, that's an if and only if. The measures that we care about, just as for Nordström is size and degree. And now it can be proven that, in fact, polynomial calculus is much stronger, it's exponentially stronger than Nullstellensatz, both in terms of size and degree. One interesting thing is that also polynomial calculus, assuming that you add these twin variables, you can also do anything that resolution can do. Okay? Remember, we have a way of translating clauses, and just to sort of a proof by picture, to see how to model the resolution step, how to resolve x or not y or z, and not y or not z to get x or not y. Note that here in blue are the two translations of these clauses. And then what you basically take, you take the complementarity axiom for the literal to be resolved over, and then you just multiply by the right monomials, and you sum up, and at the bottom, lo and behold, you get the polynomial representation of the clause that we wanted to derive. So I'm doing this very, very quickly, and the details can be checked offline, but this is a general thing, this works. And this means that if you have any small resolution refutation, you can generate a small polynomial calculus refutation also. But polynomial calculus can be exponentially stronger. For instance, sating formulas are always easy. Remember these parity principles that we talked about. If your field is GF2, the field of two elements, the onto functional pigeonhole principle with n plus 1 pigeons and n holes is always easy in any field. However, if you have only onto axioms or functional axioms or none of them, then the pigeonhole principle is still hard. So like the onto functional pigeonhole principle, which basically claims that there's a perfect matching in a bipartite graph with n+1 vertices on the left and n vertices on the right, that is easier for polynomial calculus. Other versions of the pigeonhole principle remain exponentially hard. Other hard formulas are, you can define sort of Satan-like formulas, but counting mod p for some p that is not the characteristic of the field you're in. Random KCNF formulas are also hard, except there's a slightly funny thing that usually like characteristic 2 is a challenging field characteristic for polynomial calculus. So usually proving lower bounds in characteristics other than 2 is easier than proving lower bounds in characteristic 2. So random KCNF was known for quite a while to be hard for all characteristics except 2, but it required a lot more work to get it in also characteristic 2. For coloring, somewhat recent results have shown first there were worst case lower bounds for coloring of very particular graphs. And just a couple of years ago, we had average case lower bounds showing basically that for randomly generated graphs with the right parameters, there are exponential polynomial calculus lower bounds matching what was previously known more than 20 years ago for resolution. For clique, interestingly, again, already for resolution, we didn't know much except for regular resolution. For polynomial calculus, the situation is even worse. I would say, except for some lower bounds for really, really large cliques, we don't know anything. Like, so what I'm basically saying that we believe in general that solving K-clique on with any type of algorithm should require time essentially n to the k, but we cannot rule out that maybe Gröbner basis algorithms solves the K-clique problem for moderately large K in linear time. Of course, we don't think that is the case, but we cannot rule that out. I should also say that there's an interesting parallel to resolution that if you think about how do we translate, like a clause got translated into a monomial, so width gets translated into a degree, and it turns out that you have exactly the same result as for resolution, that if we can prove degree lower bounds, then that is sufficient to get size lower bounds. And just as for resolution, you can also study other measures such as space. And interestingly, there are many results that carry over. There are many results for which we know analogous results for polynomial calculus as in resolution, but usually these results are much harder to establish. And there are also a number of very nice open problems where we believe that essentially analogous results should hold compared to what we know for resolution, but this is wide open. And for later lectures in the course, we hope to cover some such open problems. Okay, so, but this tells us, you know, if polynomial calculus is always as good as resolution, but sometimes exponentially better, then clearly we want to build SAT solvers based on algebraic methods instead. I mean, that's a no-brainer, right? Except that somehow that hasn't happened. The paper that made the connection between SAT solving and algebraic methods and Gröbner basis in '96, as far as I've understood, I wasn't around at the time, but started quite a bit of excitement, but somehow it wasn't possible to turn this into efficient algorithm. Instead, what happened at the same time is the modern SAT revolution with conflict-driven close running. There are some modern SAT solvers that perform Gaussian elimination, and Gaussian elimination is stronger than the resolution, but can be modeled by polynomial calculus, but it's a very, very limited form of polynomial calculus. One thing that I don't know is if it's like, why don't we have algebraic SAT solvers? I don't know. I don't know if it's because they're somehow harder to build, you know, maybe proof search is just harder. But it could also be that, I mean, the number of man years invested in CNF-based SAT solvers is absolutely ridiculous. And so you probably have to spend fairly substantial effort even to get to a somewhat comparable level. And I don't know if, you know, if it's could be done in principle, but it just requires work that nobody has put it. I don't. We do know that there are some settings where algebraic methods are good. For instance, circuit verification, where interestingly, this theoretical insights can be useful. Remember that I talked about dual variables and that they can make the reasoning exponentially more powerful. It turns out that this is also helpful in practice. This is a very recent paper. Okay, so what are some open problems if we want to think about Gröbner basis, SAT solving, and proof complexity? One observation is that you don't want to do Buchberger's algorithm if you want to solve SAT. And the reason for this is a Gröbner basis, firstly, it requires tons of memory and it computes too much. From a Gröbner basis, you can read off the number of satisfying assignments. But that is believed to be, like counting the number of satisfying assignments is believed to be a much harder problem than just deciding whether there are satisfying assignments. So in that sense, we believe that Buchberger's algorithm is solving too hard a problem. One other annoying thing is, one reason why polynomial calculus was originally defined without dual variables is that when you run Buchberger's algorithms, when you run a Gröbner basis computation, you have to decide for every pair of dual variables which one is larger than the other. And as soon as you have committed, the Gröbner basis algorithm would immediately remove one pair from every copy. And then you will incur this blow up that you wanted to avoid. So it's a very interesting question whether you could somehow define algebraic algorithms such as Buchberger that would somehow be, Buchberger's algorithm, except that it would be aware of dual variables and would not eliminate them, but would somehow try to keep the best copy around for every given polynomial. And if that is vague, then that's because I don't know how to do it. But I think it's a very good problem because we saw that the reference I flashed on the previous slide, there are scenarios where if we had such an algorithm, it would be really, really helpful. Okay, the only paper I know about with dual variables is that it was really a very, very hacky solution. And the problem was precisely because we're somehow capturing the Gröbner basis algorithms right when it wants to eliminate the variables and say, no, you can't do this. But it's like a very, very tailored solution. Another interesting question, if we want to connect theory and practice, is that for our theoretical analysis, the lower bounds typically use something like degree lex order. One interesting question is whether you could analyze the power of different lexicographic orders by defining subsystems of polynomial calculus and get separations. Where you could imagine, for instance, because you can, like, what would this even mean? Well, when you eliminate, when you add up two polynomials, if it's a Gröbner basis computation, there are two leading terms that should cancel. So you could sort of say, you could restrict polynomial calculus and say, whenever you add two polynomials, the leading terms have to cancel. And that would give you like an ordering aware polynomial calculus. And then maybe you could compare polynomial calculus for different orders and try to get separation results. I don't know if this has been done. I'm not aware of any work in this direction. I think this would be interesting. That's what we wanted to say about algebraic methods. Now we move on to geometric methods, more inspired by integer linear programming, where we recall that a clause could also be a clause, a big disjunction over xi's and not xj's can also be translated to 0,1 integer linear inequality by just summing up all the positive literals, summing up 1 minus all the negative literals, and saying that the sum is at least 1. And then we add axioms saying that every variable should be between 0 and 1. And then we define a proof system for this, which is the so-called cutting planes proof system that was introduced to model basically integer linear programming algorithms. So by our translation of CNF to 0,1 integer linear inequalities, we can apply this to solve SAT, but we can also apply it to any set of 0,1 integer linear inequalities, not necessarily SAT. And the rules that we're going to have are multiplication. So you can multiply any linear inequality by a positive integer. Addition, you can add to any linear inequalities. And then division. I should say, by the way, here all the coefficients are integers. And division just says I can divide by any positive integer c and then round up everywhere. And the way to see why this is sound is maybe first we can just divide without rounding and see that this clearly satisfies the inequality. Then I can do all the rounding on the left, and this can only increase the left-hand side. Once I'm done with this, the left-hand side is clearly an integer, so then I can safely round up the right-hand side also to get an integer. So a cutting planes derivation is a sequence of starting with axioms, input axioms and variable bounds, and then you can do multiplication, addition, and division. And if your derivation ends with the claim 0 greater or equal 1, that's a cutting planes refutation. Here we measure length and size. Length is the number of inequalities in your derivation. Size is when you also count the bit size of all coefficients. And now cutting planes is just as polynomial calculus. Cutting planes is exponentially stronger than resolution because you can easily, kind of a similar simulation that I flashed on the previous slide, you can simulate resolution step by step with cutting planes. Cutting planes can be exponentially stronger. For instance, for the pigeonhole principle, there are very short proofs. Basically, you just count the number of cutting planes will count the number of pigeons, it will count the number of holes, and then we'll say, well, there are more pigeons than holes. I don't think this works. Done. So cutting planes can really count, in contrast to polynomial calculus, in contrast to resolution. Though I don't think I have it on this slide, but I should say cutting planes and polynomial calculus are incomparable. So there are things that are easy for cutting planes that are hard for polynomial calculus and vice versa. And cutting planes is nice because 0-1 linear inequalities are, on the one hand, they're sort of similar object to clauses, but they're much more concise. For instance, if I want to say that summing up 6 variables, the sum is at least 3, if I have a linear inequality, I just write what I just said, whereas for a CNF encoding, you get something like this, which is like, a bit bigger. And in general, of course, if I want to say I have a sum of n variables out of which n½ is true, and unless I do something smart, then the CNF representation will just explode exponentially. Whereas I can just write it as a single so-called cardinality constraint if I have 0-1 linear inequalities. So cutting planes is powerful, and I would say like resolution by now is fairly well understood. We don't understand polynomial calculus as well, but we're reasonably good at understanding polynomial calculus. Cutting planes is really challenging. So the earliest and most well-known lower bound for cutting planes is the so-called clique coloring formulas. So we don't know whether clique or coloring, whether that's a hard problem for cutting planes. But we do know that if I write down the claim that there is a magic graph on n vertices which contains both an m clique and is m-1 colorable, then this is hard for cutting planes. So how do I write this down? Well, I have indicator variables p for the edges, and then I have the variables we had before, the q, k, v variables for cliques members, the RVL variables for giving vertices v colors L, and I write something like this, which basically says, first I say, just as before, I say there are clique members, and then here I say, well, if u and v are both in the clique, then there had better be an edge between u and v. So if this variable is true and this variable is true, then uv has to be an edge. So the clique members are neighbors. Then I get colors for all the vertices, and then I say, well, if u has color L and v also has color L, then it had better be the case that there's no edge between u and v. Okay, so clearly this formula is unsatisfiable, and we can prove if we pick parameters, m something like maybe square root n or something like this, and let n go to infinity, then this is exponentially hard. But this is a super complicated proof. Basically what you do is a technique that is called interpolation, and then you translate it into a question about circuit complexity. Basically, you argue that suppose that there is a small cutting planes proof that proves the unsatisfiability that refutes the clique coloring formula. Then from this, I can build a small circuit that is very good at distinguishing cliques. And then I prove separately that, well, such small circuits don't exist, well, that tells me that there couldn't have been a small cutting planes proof in the first place. And now I get a lower bound. So it's like a very roundabout way, and you have to go deep into circuit complexity and prove highly non-trivial results there. And as I said, we really don't understand cutting planes. We need to develop new proof techniques. It's interesting that in the last few years, there have been some developments. But just to mention some open problems, some recent developments and open problems. Random KCNFs we saw are hard for both resolution and the polynomial calculus for constant k. For cutting planes, we have exponential lower bounds for logarithmic width, but it's a big open question to get this down to, say, random 3CNF formulas or even random KCNF for any k, even for k being 1,000,000. It would be amazing to prove lower bound for cutting planes. Interestingly, for a long time, Sating formulas, these graph handshake lemma formulas, were believed to be exponentially hard because somehow cutting planes can't really do parity, except that apparently it can, because Sating formulas have not polynomial size refutations, but quasi-polynomial size refutations. So not polynomial, but something like scaling like n to the log n or something like this. So almost polynomial. And we don't have any lower bounds for coloring or cube. Again, same questions if we move over to theory. So cutting planes is exponentially more powerful than resolution. So why don't we build SAT solvers based on cutting planes? Now, in contrast to algebra and algebraic methods, this is actually something that is being actively explored. So there are so-called pseudo-Boolean solvers that try to do this. But it turns out that it's really hard to make these formulas competitive with CDCL SAT solvers. So let's just very quickly, we don't really have time to talk about this, but one thing that happens, like a lot of the data structures and heuristics get more complicated. Clauses are simple objects. 0, 1 integer linear inequalities with arbitrary integer coefficients are much more complex. So a SAT solver spends a lot of its time just detecting forced variable assignments, so-called propagations. That's much more expensive for linear inequalities. Also, when you're computing, you don't want the integer coefficients to explode, because then your integer arithmetic is going to be really slow. And you're going to get, for comparing clauses is kind of easy in the sense that, well, if a clause is smaller than another clause, then it kind of maybe looks better. But how do you compare two different 0, 1 linear inequalities, which maybe one has few variables but constrain them in a weak way, and another constraint has much more variables but constrain them much more, and maybe a third constraint is weaker still but has small integer coefficients, so it will be faster to operate with. There are many more parameters that are hard to figure out. And precisely because cutting planes is a much more powerful method of reasoning, that means that you have more degrees of freedom. So how to design conflict analysis for cutting planes, for instance, is a highly non-trivial question that is not well understood. And the most embarrassing problem of all is the way we know how to do so-called pseudo-Boolean solving today. If you feed a pseudo-Boolean solver a CNF formula, then it just collapses the CDCL SAT solver, except with very expensive data structure. So if you want to kill a pseudo-Boolean solver, give it a CNF. This is very, very annoying, and it would be really nice to do something about it. So basically what you would want to do is, I'm getting a CNF formula, maybe let me see if I can rewrite it to a nicer representation. But doing that is not entirely obvious what that would mean in general. And again, we don't know whether it's really truly harder to build pseudo-Boolean solvers, or if it's just that so much more work has been put into CDCL. Here I would actually, my personal opinion would be, I think we've just done too little work. I mean, in the Meow group, we are trying to develop pseudo-Boolean solvers. There are things that could be done. I do believe that pseudo-Boolean solvers could be made competitive with and better than SAT solvers, but I do believe that we need more than just a couple of research groups working on this. So some algebraically motivated questions. So the rule we had for cutting planes, the rule that does like Boolean reasoning is the division rule. It turns out that in another rule that people use that mixed integer programming people would call maybe coefficient tightening, that some people call saturation, is, well, suppose we have a constraint in normalized form, meaning that it's a positive linear combination of literals, then in that format, without loss of duality, no coefficient needs to be larger than the right-hand side. So you can define a saturation rule that just truncates all coefficients on the left-hand side down to the right-hand side, so-called the degree of falsity. And that actually gives you a complete decision procedure for feasibility. In the complexity literature, we're using division, but early pseudo-Boolean solvers actually use saturation. Now, this raises a question. As a theory person, you can say, I can define cutting planes, except that I can remove division and put in saturation instead. And then I can compare different methods. Now, one thing that is obvious here, one question that often arises, like, why don't I take both? And this is a good question, but often you have to like commit which rule goes first, because they don't necessarily commute. So it's a meaningful question to ask how cutting planes with saturation compares to cutting planes with division. And this is, again, open. We know that cutting planes with division can be stronger. And it seems like division is most often preferable in practice, but we don't know. So here's one like very concrete question. Consider the even coloring formula. So every edge, again, is a variable. And I have a graph where every vertex has even degree. And now I just write down constraints saying that every vertex sees exactly half of the variables true and exactly half false. So this is this formula here for this particular graph. Now, if you look at this, you realize that this is actually satisfiable. It's hard to do really interesting unsatisfiable formulas. They will be unsatisfiable precisely if the total number of edges is odd. And these are so-called even coloring formulas. It's not so hard to see that these are trivial for tree-like cutting planes. Basically, you just sum up all of these and divide, sum up all of these and divide, and then sum again. Done. Super trivial. If you translate this to CNF in the canonical way, you just take every linear inequality and write it as a collection of clauses, then it will be exponentially hard for expander graphs. And this means also that if I take the CNF representation and feed it to a pseudo-Boolean solver, it will also be exponentially hard. But now I can try with this so-called pseudo-Boolean encoding instead and see what a pseudo-Boolean solver does with that. And now the answer is that division-based solvers seem to do much better than saturation-based solvers. Although even for division-based solvers, at least back in 2018, these formulas were seriously challenging. So here's a theoretical question. Is it possible that these formulas actually separate cutting planes with division from cutting planes with saturation? I don't know. Or, could we find another separating example? I think this would be interesting. Another interesting question, if we go beyond clique to a more general subgraph isomorphism problem, I have a pattern graph, and I want to know if the pattern graph P embeds isomorphically into the target graph T. The clique problem is just when P is a clique. Okay? So in general, what does it mean as a subgraph isomorphism? Well, I have to map every vertex A in the pattern to some U in the target in such a way that if AB is an edge in the pattern, then they have to map to an edge in the target. Okay? Again, this is clearly NP hard, except that there are really good subgraph isomorphism solvers out there. So if you have like a practical subgraph isomorphism problem, chances are you can solve efficiently. Now we can write this also as a collection of 0-1 interlinear inequalities. Basically, here I say that, well, every pattern vertex A has to map to a target vertex, but only one. And the mapping is 1-to-1, so no target vertex U can receive several pattern vertices B. And then the only constraint that is slightly non-obvious is that edges map to edges. So what does this constraint say? Well, it says that either A does not map to U, and then we're clearly off the hook because the rest is positive. But if A maps to U, then for some neighbor V of U, it has to be the case that B maps there if AB is an edge. Okay, so now I'm doing this a little bit fast, but hopefully it's believable that there is a subgraph isomorphism. There is a subgraph isomorphism from P to T if and only if there's a satisfying assignment to this. Okay, are you buying this? Kind of? Maybe, because it's getting late in the day, so you're buying this just to get out of this room. Sounds good. So now, why do we care about this? Well, the interesting thing is I told you that there are amazing subgraph isomorphism solvers, like the Glasgow subgraph solver. It turns out that if you look at what this solver does, it's formalizable within cutting planes. So if the Glasgow subgraph solver runs fast, it will, and if there is no subgraph isomorphism of P into T, then it will generate the cutting plane's proof in size proportional to the running time. Again, we don't know, like currently we have no idea, like does the Glasgow subgraph solver solve subgraph isomorphism in polynomial time? Probably not. Okay. Can we prove that it doesn't? No, we can't. Except if you guys would come up with families of P's and T's for which you give lower bounds for this form. Yeah. Is this hard? I have no idea. I don't know if anyone has thought about this. I think it's a nice open problem.
In particular, click would be.
Say again?
In particular, click would be.
Click would be amazing. Yes, if you can do click, yes. But somehow the idea would be that click is sort of we can't even do it for resolution, right? So maybe start with the resolution and then try to extend. But here the point is that you could potentially it's perfectly believable here that you could play with the pattern and the target graph. Like maybe you could. Okay, we haven't talked about this in this lecture, but maybe you can do some lifting techniques, find some nice gadgets, reduce from some other problems. Like anything is fair game, right? As long as the end result looks like this.
So when you're saying do it first for resolution, so what kind of lower bound you're looking for?
For a click for resolution?
No, for this one.
For this one. Oh no, that's a good point. Like I haven't thought about resolution for this one either. I don't know what hard examples would be. For resolution, I think I'm still like, I think we should be able to do click lower bounds. We're morally very close. I mean, sort of, the click problem, regular resolution can do as well as general resolution. There should not be any difference, except, we can't prove. But here I would think about let's think about all of these fancy techniques in let's see, where are we? Here these references. Let's look through these papers. There are a lot of gadgets and lifting and stuff, and can any of this be used to address this problem? And again, I don't know, maybe it's that hard, or maybe it's just trivial, like a really embarrassing gadget direction. I don't know. I just think it's a good problem. I haven't thought about it. Okay, so we're almost at the end. So again, what are we going to do in the proof complexity lectures? We're going to talk more about resolution, about polynomial calculus, about cutting planes, and we're going to focus on all of these lower bounds and this weird interpolation methods with connection with circuit complexity. We're going to talk about those. We're going to talk about resolution lower bounds. We're going to see how much more painful polynomial calculus lower bounds are. Now, in the few minutes that remain now, I'm going to say something briefly about proof system that we will mostly not talk about, but that are still algorithmically relevant. So here's Nullstellensatz again. Let's fix our field to be R, the reals. And again, we have some input polynomials. We're insisting on Boolean solutions. And Nullstellensatz certificate of unsatisfiability and Nullstellensatz refutation is this kind of thing. Except that if we can do it, you will agree with me that if I insist on doing -1, you're fine with that, right? I mean, it's no big difference. You're fine with this? So let's define Nullstellensatz as proving -1 instead. Why do I do this? Well, because now suppose I relax this a bit. Like maybe it's hard to hit exactly -1, but suppose I can give you a certificate that here's the Nullstellensatz certificate, the QIPIs and the RJs and XJs, except let me allow to add some, the name for these are conic juntas. It's just a fancy name for, I'm basically multiplying literals by some positive coefficient. What you will realize now with what can we say about this alpha k times 1 minus xi times xj? Clearly it's not negative, right? It's either 0 or it's positive. So it can only take me further away from -1. Okay, so if I can write a certificate like this, you should definitely be confused. You should not be confused at all. You should be convinced that this is a certificate of unsatisfiability. But note that this gives me a little bit of wiggle room now. I don't have to hit -1 exactly. So it might be easier. I'm getting a potentially more powerful proof system now. This proof system is called Sherali-Adams. So this is a Sherali-Adams certificate of unsatisfiability. Okay. Now I can go even further. Suppose that, again, here's my Nullstellensatz certificate, and I'm allowing you to add any sum of square polynomials. And I'm hitting -1. Why is this more general? Well, you realize because x squared is equal to x, these are, without less of generality, also squares, actually. The 1 minus xj, xi times xj's. But in general, let me just sum up any squares. And if I'm still hitting -1, clearly this is a certificate of unsatisfiability. Now I have even more flexibility, which means that potentially, I don't know, but potentially proofs could be even more efficient. This is sum of squares. Okay. We'll maybe talk a little bit about Sherali-Adams. I don't expect us to talk at all in this course about sum of squares. It's a very exciting proof system though, so it's definitely worth studying. So in terms of algorithms, Sherali-Adams models what you can do with linear programming plus strengthening your LP systematically by adding constraints that you get from LP hierarchies. In the same way, sum of squares models what you can do with semi-definite programming plus adding extra constraints to sort of tighten your program formulation. And fixing, again, you realize that now once we have this description with squares and these cones, it's kind of important that we're over the reals, because it doesn't really make sense what a square is if you're not over the reals. So Sherali-Adams and sums of squares are defined only over the reals. Over the reals, you have a strict hierarchy from Nullstellensatz being less powerful than Sherali-Adams, being less powerful than sum of squares. Over R, over the reals, sum of squares is strictly stronger than polynomial calculus, whereas Sherali-Adams and polynomial calculus are incomparable. And all of these results are in a very nice paper by Berkholz. But now what you need to be aware of also is that with polynomial calculus, you can start playing with the fields, and there are fields for which polynomial calculus would be better than sum of squares. So I won't say much about sum of squares, except that it is a very strong proof system. It can reason efficiently about the pigeonhole principle also. Many of the best theoretical approximation algorithms for approximately solving NP-hard optimization problems that we have can be modeled as sum of squares algorithms. So it's like sum of squares really captures most of what we know about state-of-the-art approximation of NP-hard problems, at least on the theory side, except that there are some blemishes. For instance, sum of squares cannot do parity reasoning efficiently. It really sucks at Sapien formats. And there's a wonderful survey by Noah Fleming and co-authors that is highly recommended reading if you want to know more about this. Another proof system that incidentally also Noah Fleming has worked on is stabbing planes, which is meant to model modern 0-1 integer linear programming in full generality. I'll only give a very quick description. Basically, you have some kind of polytope, so a set of linear inequalities. If your polytope is empty, like it has no real valued points, then you're done. You've refuted this branch and you can terminate. Otherwise, you pick any linear inequality over literals and you branch. In one, you add that this linear form is greater equal A. And in the other branch, you add that, well, the linear form is less equal A minus 1, where all of the coefficients that you see here are integers. So it's called stabbing planes because you're sort of removing the plane between A and A minus 1. And this allows you to cut out more and more of your polytope. And when finally you can cut away all your branches, then you're done. And the number of nodes in the search tree is the length of the proof. And again, just as for cutting planes, the size of the proof is if you also count the bit size. Okay, and it might not be obvious, but it's not hard to show that stabbing planes is actually at least as strong as cutting planes. And if I think when the paper was, when stabbing planes was introduced like 7 years back, I think the feeling was that clearly it must be much stronger. Except that then there have been some somewhat surprising results saying that actually, as long as your stabbing planes inequalities do not have too large coefficients, you can actually simulate them in cutting planes with at most a quasi-polynomial blow-up. Except that the cutting planes coefficient can become very large. Also, it turns out that these slightly weird interpolation-based lower bound techniques that you can do for cutting planes, they also work for stabbing planes. So now we're like almost at a setting where, well, we don't really know, like all the lower bounds we have for cutting planes, which aren't too many, but some, sort of carry over to stabbing planes. And we have a semi-efficient simulation. So we really don't know. I mean, I still think it's reasonable to believe that stabbing planes should be asymptotically stronger than cutting planes, but it's already clear that this might not be so easy to prove. And there might not be an exponential separation. So this is something very interesting. We probably won't be able to talk about stabbing planes, unfortunately. But let's see. The final proof system I want to talk about, going back to resolution, going back to SAT solving. Recall that the resolution rule was just saying that from two clauses you can get the resolvents. The extension rule introduces, it's a way of taking a variable A that hasn't been mentioned before, and you just introduce three clauses that define A to be exactly, take the truth value of X and Y. This is what these clauses mean. You see that if X and Y are both true, this forces A to be true. But if X is false, that forces A to be false. And similarly, if Y is false, that forces X to be. If Y is false, that forces A to be false. And now if you take the resolution proof system and you just add this rule that, well, you can always introduce a new variable A and these three clauses, how much could possibly happen? Turns out that this is a complete game changer. Okay? It turns out that, firstly, this is extended resolution is very similar to, but not exactly the same as, the so-called DRAT proof system that has been used to formalize proofs of correctness for SAT preprocessing techniques. And DRAT is the most well-known proof system that is also used for SAT proof logging. And DRAT and extended resolution are in fact as strong as the so-called extended Frege proof system, which is like incredibly powerful. It's way beyond anything we've talked about today. So resolution plus just this three clauses for a new variable is incredibly powerful. And the point is that you don't just do this once. You introduce a new variable A, and then you introduce a new variable B, and maybe the defining clauses for that variable can use A. And then you define a new variable C in terms of A and B, and sort of you can use this in resolution to build up. The way to think about it, you can sort of almost build up Boolean, like arbitrary Boolean circuits, and then apply reasoning on those circuits. And that turns out to be super powerful. Which raises the question, then why don't we base SAT solvers on extended resolution? And the answer is people have tried, but it's hard to get it to work. It's hard to get a good heuristic for when to introduce variables. And it's also hard to get the SAT solvers to pay attention to these new variables and branch on them in a good way. And now the situation with SAT solving is that if I want to model faithfully everything that a modern SAT solver does, then I would need also to analyze extended resolution proofs, and lower bounds for SAT solvers would require lower bounds for extended resolution and extended Frege, and we're nowhere close to that. That's like way beyond. Lower bounds even for Frege without extension variables would be a major, major breakthrough. So somehow, if we wanted to analyze SAT solvers with preprocessing, we cannot use full extended resolution. We would somehow need to pin down some more restricted version of extended resolution and analyze what resolution with these restricted form of extension does. How would we do this? I don't know. I don't know. And unfortunately, I think it's hard to do because this introducing new variables, exactly as I showed here, is in fact one of the things that SAT solvers will sometimes do. It will do it in only very specific cases, but it will do this. And already that sort of buys you, that gets you to the, if you allow this, maybe you could limit the depth of these extensions. So you can only do it like a few times or something like this. But yeah, I don't know. So this is a very powerful proof system. But it's still fair to say that if you run a modern solver with preprocessing and you give it like something that is hard in theory, like one of these crafted benchmarks, one of these combinatorial theory benchmarks we talked about, most of the time, the exponential lower bounds seem to hold. So like basically modern SAT preprocessing techniques are nowhere close to realizing the power of extended resolution. This brings us to the end. So if you are interested in more reading, the Handbook of Satisfiability is a good references for the applied side of things. It's the state of the art as of 2021 for all kinds of SAT-based techniques. And there is in particular the 7th chapter in the handbook by Sam Buss and yours truly is trying to give, it's essentially an extended version of what I told you now, trying to describe different proof systems and explaining how they translate, like what is the connection to different combinatorial solving algorithms. If you want to go hardcore into proof complexity proofs, though, you should not look at the Handbook of Satisfiability. You should maybe read Proof Complexity by Jan Krajicek, or you should attend, the lectures that we're going to have in this course. So this brings us to the end. So what did we do today? We have looked at proof systems that are used for combinatorial solving. We talked about resolution, which corresponds to modern conflict-driven SAT solving. And we've talked about Nullstellensatz and polynomial calculus and how that corresponds to algebraic methods, such as Gröbner basis computation. We talked about cunning planes, how it corresponds to pseudo-Boolean solving. Very briefly at the end, I sort of flashed Sherali-Adams, LP linear programming hierarchies, sums of squares, semi-definite programming hierarchies, stabbing planes, which is 0-1 integer linear programming, and extended resolution, which is what you need to fully model all types of SAT pre and inprocessing. One thing, by the way, that I didn't mention at all, that is completely missing from these slides, and that would be really, really nice, is if you look at many of the benchmarks that we had, for instance, the pigeonhole principle, if you would just have a notion of symmetry, then clearly the pigeonhole principle trivializes, right? You say, well, I have n+1 pigeons, they need to go into n holes, everything is symmetric. Without loss of duality, pigeon 1 goes into hole 1. Now I have an instance of the pigeonhole principle with n pigeons and n-1 holes. Without loss of duality, pigeon 2 goes into hole 2. Keep going, and without loss of duality, I see that I run out of holes. Also for the clique coloring principle, where you say, I have a magic graph, where there is an m clique, but it's m-1 colorable. Again, without loss of generality, shuffle your graph around so that the clique are the first m vertices, and then just look at that and prove that, well, you have too few colors for these vertices. So the problem with this is it's kind of, so what would be really nice, because there have been developments, especially in the last few years, which have really, really good symmetry handling techniques. We are not at all mirroring that in proof complexity. So it would be nice to have sort of definitions of polynomial calculus, resolution, cutting planes that sort of also has a rule for symmetry. Except for refutational proof system, you have to think a little bit. Firstly, you have to think a little bit about what that means. And secondly, it seems like the proof techniques we have currently would sort of completely break. Thank you. So I think this is like, if we wanted to be really algorithmically relevant, having what I told you about today, but also being able to model symmetry would be really, really nice. I should have put this on the slides. I realize now as we're getting to the end of the lecture that I did. But I think with that caveat that I should have had a slide or two on symmetry handling and didn't, except for this, I think this is at least for resolution, polynomial calculus and cutting planes, I think this is basically state of the art in connections between theory. And I've tried to argue that proof complexity can be a useful tool to analyze these state-of-the-art algorithms. And also what I didn't tell you about is that can also help improve these methods and give proof logging methods for certifying correctness, but that would be a different course. Above all, I think, and our main excuse for doing proof complexity in this research group, I think, is just that, well, more than anything else, studying resolution, Nordström polynomial calculus, cutting planes, and other proof systems just gives rise to very, very nice mathematical problems. And understanding how powerful these different methods of reasoning are, that forces us to work on very intriguing and challenging and fun combinatorial problems. And that is what I hope to do in the proof complexity course that we will run this winter. But now we've reached the end of this introductory lecture on proof complexity as a computational lens. So thank you.